Welcome to another episode of Schmidt Chem. So we're looking here in topic 5.1 of AP chemistry, looking at reaction rates. We're also going to be looking at topic 5.5, the collision model. These two topics kind of go together so hand in hand that we can't really separate them. And so in looking at our reaction rates, we're supposed to explain the relationship between the rate of a chemical reaction and experimental parameters. And we have to start off with looking at kinetics of a chemical reaction and its definition being the rate at which the amount of reactants is converted to products per unit of time. And so rate is always going to involve the element of time. And so we're looking at that. And then we're looking at the rates of change of reactants and product concentrations, and they're determined by the stoichiometry in the balanced chemical equation. And so we're going to write rate expressions for reactions based off of the stoichiometry of the reactions. And then we're going to spend a lot of time looking at the rate of the reaction and how that is influenced by reactant concentrations, temperature, surface area, catalysts, and other environmental factors. And this last part on 5.1.8.3, that is where we see the incorporation of the collision model. Because as we are making changes to concentration, temperature, surface area, and catalyst, we have to think of these in terms of the collisions that are taking place within the reaction and to see if the reaction will even take place. And so that's where we get into the collision model, and we're explaining the relationship between rate of an elementary reaction. We'll talk about elementary reactions a little bit later on, explain what that is. But we're going to explain the relationship between the rate of a reaction and the frequency, energy, and orientation of particle collisions. And we're going to spend a lot of time on that. And some of these other ideas that you see expressive there under essential knowledge, you should be somewhat familiar with. And so let's go ahead and go to our notes. And we're looking at this first section. And what we're going to do there is we are going to define chemical kinetics. The kinetics of a chemical reaction is defined as the rate at which the amount of reactants is converted to products per unit of time. And so here we're looking at the reaction rate as a measure of how quickly the concentration. And that's kind of a big deal because when we're looking at reaction rates, what we're actually looking at is a change in concentration. And so we're going to look at how quickly does the concentration of the reactants decrease while the concentration of products increases. And then look at this over time. We have that time element because we're going to be looking at rate, and we're looking at the change of something over time. In this case, the change of concentration over time. And so mathematically, the average rate of a reaction over time interval is expressed in terms of the change in concentration over time. And you see this equation that I have written here. And so what we see there is there's some unique characters that maybe we are not familiar with. And so we see what we're going to do is we're going to go over those, and we're going to look at some of my bad handwriting, but we're going to make sure we understand this. Anytime we see this bracket around a symbol, around an element, around a chemical formula, it's representing that we are looking for the concentration of that substance, of that species. And so when you see the bracket, you should be thinking of concentration. Now, there are several ways of expressing concentration. In AP chemistry, we land on molarity. So we're going to be looking at the concentration in terms of molarity, and that's what we use for a bracket. For instance, if I say I put a bracket around A, I'm saying I want the molarity of substance A or the concentration of substance A. Another term or another thing that you may not be familiar with is the delta sign, and that's just looking for a change. And what we're going to be doing there is, in order to determine the change, we look at the final value minus the initial value. So for instance, if I want to find the change in the concentration of A, well, then I'm going to take the concentration of final minus the concentration initial. And then lastly, a change in time is the final time minus the initial time. And so as long as we're familiar with those expressions, we should have no problem being able to solve problems. But those are some things that we needed to clean up so that we can even understand this equation. We understand that now that the rate we notice is equal to the change in the concentration of substance A. So how do we know that's concentration? Because it has this bracket over the change in time. And so if we look at this and we wanted to spell this out, this would be the rate is equal to the concentration of A final minus the concentration of A initial. And this would be over the change in, not the change, excuse me. This would be over T final minus T initial. All right, and that's what we get there. And so at the end of the day, we're going to end up with some units. We're going to end up with units of concentration, and that's going to be molar per, and the time is usually expressed in seconds. And so rate typically has the units molar per second. That's a big M referring to molarity, molar per second. Now, on your resource sheet, you might see it, molarity. It could be expressed as moles times liter to the -1 times second to the -1. And what that means is simply this. It means moles per liter times second, which is molarity over second. So that's what that is. It means the same thing, but molar per second or molarity over seconds. And so those are the standard units for rate of a reaction. And then by convention, the rate of the consumption of the reactant is given a negative sign. And so what happens is, if we look at our graph here, what we see is at time zero, we see that the reactant concentration is high. But as time goes forward, the concentration of maybe I'll use a highlighter, the concentration of the reactant decreases. So we see it decreasing, and that's not a highlighter, but it sees it decreasing over time. And so that is what we're going to see a negative value, because when we look at change, let's say we looked at here, we wanted to find, there's this point here, we would call this TF, and we might start at initial, this would be TI. Well, we can see that the final concentration is much lower than the initial concentration. And so if we take a value that is smaller and subtract a larger value, we're going to end up with a negative value. And so what we're going to see there is when we're looking at a reactant, the change is often going to have a negative sign because the concentration of the reactant is decreasing as the reaction moves forward. All right, and we're going to see that when we write our rate expressions as well. All right, another thing that we see is that the rate of the formation of the product is positive. And so we would see, for just like we just saw, the product concentration at a certain time versus the initial. So TF here minus TI, we see that TF would be a larger value than the initial. And so that would end up with a positive change. And so for that reason, we see that the products end up having a positive change in concentration over time. All right. However, it is important to note that the overall reaction rate is expressed as a positive value. And we're going to see that as we write our rate expressions as well. So another thing that we see here is, if we were to look at this reaction here, we want to kind of see and compare maybe what is a fast rate versus a slow rate. We notice that both of these reactions are occurring over the same amount of time, but we see that in this A plus B going to C, that all of the reactants get converted to product In the same amount of time, the reaction of X and Y to Z, only a small fraction of the particles of the reactants get converted to products. And so we would say that this one is slower and this one is faster. And we also have that labeled here, faster and slower. And that's just based off of the amount of reactants that react to form products in a given period of time. What is the change in concentration of the reactants and the change in the concentration of the products with regard to time? If the change is greater in a smaller period of time, well, then we know that it's faster. If the change is lower in a given period of time, then we know that the rate is slower. And so that's what we're looking at there on this page here. So we're going to move on to the next page. And this moves us into our second piece of essential knowledge. And this says that the rates of change of reactants and product concentrations are determined by the stoichiometry and the balanced chemical equation. And so here we have a generic equation. And notice on this equation that these lowercase values are representing the stoichiometric coefficients. And so we have to account for these the stoichiometry of the reaction in writing the rate expression. Now, when we write this rate expression, we are actually getting the average rate over a given period of time. All right, but we have to set these things equal using stoichiometry. And one way we do that is we take the coefficient and we take the inverse of the coefficient and we multiply it by the expression for that reactant. For instance, we see that we have A and we want to find the rate. Well, we say, okay, well, I know about rate. Rate is the change in concentration with regard to time. Well, in this expression, I have to make sure that I am taking care of the coefficients, because I am saying that the rate of this expression is equal to the rate of this expression, which is equal to the rate of this expression and this one. These are all equal to rate. And the only way they're going to be equal is if we are considering their stoichiometric coefficients. All right. And hopefully we can make a little bit sense of that in a minute. But how do we express these stoichiometric coefficients? First of all, we take the inverse of those. We take the inverse of those, and what we're getting is, instead of writing A, 1 over A. And then you also might notice that we have a negative sign. And this negative sign is absolutely important for this expression, because the change of A, as we just talked about, is going to be a negative value. And so because the change in A is going to be a negative value, remember, reactants are decreasing with time, so the final concentration is going to be much less than the initial concentration. And so if we did not have this negative sign in our expression, if this negative sign was not there, then we would end up with a negative rate for the reaction, and that's not possible. We have to have a positive rate. And so this negative sign helps make the rate positive. So we have to have, for reactants, a negative sign in the expression, because the change in the concentration of reactants is always going to be negative for a reactant. Okay, and then we go into B and we see the same thing. It's 1 over B, lowercase b being the coefficient. Again, we notice that it's a negative sign. Why is it a negative sign? Because B is a reactant, and the reactant concentration is going to be a negative change with regard to time, meaning that the final concentration is going to be lower or a smaller value than the initial concentration. But notice as we go to products, and this is not absolutely necessary to express, but they have a positive sign. And the positive sign here is just for contrast. It's not something that you have to express, but the change for products is going to be a positive value. And that's a big deal, because we do not need to have a negative sign there to account for some negative value here, because this is going to be positive. So the final concentration is always going to be greater than the initial, which then is going to yield a positive rate. So we don't need to put a negative sign in the expression so that the rate will come out positive. It will just naturally end up that way. And so we see the same thing for d, 1 over lowercase d, it's a positive value. Now, what does this look like in an actual equation? When we look at an actual equation, as we see in this example with the NO2, we notice that it has a coefficient of 2. And so we took the inverse of that and we said, oh, that's 1/2. All right, so we multiply our rate expression. The rate expression is the change in NO2 with regard to the change in the concentration of NO2 with the change in time. But in keeping with accounting with the stoichiometry of the equation, we take it 1/2, and then in making sure that our rate is going to end up positive, we have to give that a negative value in that expression. So the rate expression with regard to NO2 is negative 1/2 the change in concentration of NO2 with regard to the change in time. All right, and so we look at this next part and we see the product, and this says 2NO. Once again, we take the inverse of that, 1/2. Notice now this is a positive value. The positive does not have to be shown, but we notice that it is going to be a positive value because it's a product and the final concentration is going to be greater than the initial concentration. And then we look for O2. It does not have a coefficient, so we did not need to add anything to that. All right, so that's how we write the rate law expressions. Now we're going to see how those relate and how the stoichiometry actually plays out in this and doing this example of completing the table. Now, while this example does not tell us to write the rate expression for all of the or for each of the reactants and products in the balanced chemical equation, we're going to go ahead and do that, and then we're going to use that in our table and solving for these problems. Okay, so when we write the rate expression here, we're writing rate is equal to, and now we're looking at Cl2, and we notice it's a reactant, so we're going to put in negative. We notice it has a coefficient of 1, so we don't need to really do anything there. So we're going to just write this as the change bracket to represent the concentration of Cl2 with regard to the change in time. All right, and so that's what we see there. Then what we're going to do is we're going to set that equal. We're going to set that equal to the F2. And we notice that it also is a reactant, so that's negative. It has a coefficient of 3. Inverse is 1/3. And then we're going to put in the change in concentration of F2 with regard to the change in time. All right, and then lastly, we're going to do the product. We notice it's a product, and so we are not going to put a negative sign in this expression, nor do we need to put a positive sign, but if you want to, it's perfectly okay. So we're going to then say that this is 1/2 the change in the concentration of ClF3 with regard to the change in time. And so there's our rate expressions for that reaction. And that is setting everything equal. Notice that rate is equal to, I don't know what that's going on, but rate is equal to that expression, and that expression. They're all set equal to rate. And so each of those expressions equals the rate. So that means the rate for all of those expressions is exactly the same, and they're going to end up being exactly the same because the stoichiometry of the reaction is considered. What that does not mean that the change is what that does not mean is that the change in the concentration of those reactants with regard to time is equal. While the rate is equal, their changes are not equal. And we're going to see that in this table. So in this table, we're noticing that we are not entering coefficients into this expression. We are simply just asking for the change in the concentration of F2 with regard to the change in time. And we see the same thing for ClF3. We also see that we're asked to find the rate. Another thing that we would notice is that this is asking for the change in concentration of Cl2 with regard to time, and that it is giving us a negative value. If that was the rate, well, that would be incorrect because the rate is not going to be a negative value, but the change in the concentration of CO2 with regard to time is a negative value. Okay, so let's go ahead and apply some of this ideas. And the first thing that I'm going to solve for on this is rate, because I find that if we find the rate, everything else is way easier to solve. And so let's go ahead and find the rate. Now, the only information we have is the change in concentration of CO2 with regard to time. But we also know the rate expression for that substance. We just wrote it, and that is equal to the change in concentration of CO2 with regard to the change in time. And so what this is already telling us is that that value is negative 0.012 molar per second. So as we apply that to our expression, we say negative times negative 0.012 molar per second. And that actually gives us a rate of 0.012 molar per second. And so our rate is actually a positive value. And this is why we have a negative in our expression. So because this change here is going to be negative because it's a reactant. Its concentration is decreasing with regard to time. And so we see there that, in fact, if we did not have that negative sign there, that our rate would not end up positive. And here it does end up positive. All right. Now we come down to, let's figure out how do we find the change in concentration of F2 with regard to time. So if we want to do that, what we could do is we could take our expression here and we can solve for the change in concentration of F2 with regard to time. And so I'm going to rewrite the rate expression, and that rate expression is equal to negative 1/3 the change in concentration of F2 with regard to the change in time. But we're not interested in the rate. We're interested in all we're interested in, let me highlight this, all we're interested in is this expression right here. So let's rearrange this equation to solve for that expression. When we rearrange this equation to solve for that expression, what we would get is delta, the change in concentration, all right, over the change in time, is equal to rate, and then we have to get rid of this 1/3, so we're going to multiply by -3. And when we do that, we're going to see we already know the rate. The rate is 0.012 molar per second, and then we're going to multiply that by -3, and we're going to end up getting negative 0.036 molar per second. And make sure, especially for your grader, and I'm doing this for you too, make sure that we have a big M, that it's a noticeable that it's referring to molarity. So what we notice then is that this is a negative value, and that also we should notice that it's 3 times greater than the change in the concentration of Cl2 per second. And so why is that? Well, we notice that the coefficient of F2 is 3, while the coefficient of Cl2 is 1. And so when this reaction is taking place, it takes 3 moles of F2 to be used for every 1 mole of Cl2. And so, of course, the concentration or the change in the concentration of F2 with regard to time has to be greater because Cl2 cannot be consumed any faster than this stoichiometric ratio allows for. And so we see that it is 0.036 or 3 times the value of Cl2 with a coefficient of 1. All right. And so we can definitely use our brains on this, and we don't have to necessarily do a whole bunch of math. Once you know the rate, you can apply the rate to the stoichiometric coefficient. All right, and so that makes that real easy. For instance, we know the rate is 0.012 molar. So now we know the change in the concentration of ClF3 is 2 times the rate. And so the change in ClF3 is going to be 0.024 molar per second. And notice that's a positive value. And why is that? It's because it's a product. And if we did the same thing and we wanted to solve this algebraically like we just did for this other, we would end up with that same value. All right, and so we can go ahead and do that real quick. So we have our rate expression being, rate is equal to 1/2 the change in the concentration of ClF3 with regard to the change in time. Now, again, they're not wanting us to figure out the rate. We just want to solve for this expression right here. Notice that's the same as that. And so what we end up with when we rearrange our equation is the change in concentration of ClF3 with regard to the change in time is equal to rate. And then we have to multiply by the inverse of 1/2, which is 2. And so rate is equal, or the change in the concentration of ClF3 with regard to time is equal to rate times 2, or 0.012 molar per second times 2, which is equal to 0.024 molar per second. And so, again, that's what we got. We did that in our head before we did that algebraically, and hopefully that helps you with those. You have some of those on your assignment, and hopefully that will help you get all of those correct. All right, then the next part of our lecture here is we're going to go over an example, and we have some of this in our worksheet as well. And so what we're supposed to do is consider the following decomposition reaction of N2O5 into NO2 and O2. And we're supposed to express the rate of the reaction in terms of the change of concentration of each of the reactants and products. And we can do that real easily because we're experts at this now. We can say rate is equal to, we know this is a reactant, so we're going to say negative. We know it has a coefficient of 2, so we're going to take the inverse of 2, which is 1/2. And then we just write in the change of concentration of N2O5 with regard to the change in time. And then we set that equal to, notice this is a product. It has a coefficient of 4, so to 1/4 the change in concentration of NO2 with regard to the change in time, which is equal to, notice no coefficient and a product, to the change in concentration of O2 with regard to the change in time. All right. And so that's what that looks like. And that's as simple as that is. All right. And so the next part it's asking us in B is in the first 50 seconds of this reaction, the concentration of N2O5 dropped from 0.8 molar to 0.65 molar. Calculate the average rate of the reaction during this time interval. All right. So the average rate of the reaction during this time interval. And so what we're given is data for N2O5. So we're going to want to use the rate expression for N2O5. And so we start off by writing the rate expression for N2O5, which is rate is equal to negative 1/2 times the change in concentration of N2O5 with regard to the change in time. Now, how did we determine what change is? Remember, we said change is final minus initial. And so what we're going to then do is plug in our values. Our final concentration for the N2O5 was 0.650. Now, we can't forget to add this or to incorporate this negative 1/2, but this is equal to negative 1/2 times 0.650 molar minus the initial concentration, 0.800 molar. And then we're going to do that over time. Now it says in the first 50 seconds. So the time final was 50 seconds, and the time initial was 0 seconds. And so we just plug that into our handy dandy calculator, and we will get that solved. And what we should get here is we should get 0.015. Sorry, that's incorrect. Wrote that down wrong. We fix that. 0.0015. Make sure that decimal's in there. Molar per second. All right, 0.0015. Let me write that again. 0.0015 molar per second. That way it's a little more clear. And so that would be the average rate of the reaction. All right. Now, they're asking us, well, if the volume of the reaction vessel in part B was 2 liters, what amount of O2 was formed during the first 15 seconds? During the first 50 seconds of this reaction. And so we have the rate of the reaction, but we need to figure out what will be the concentration of O2 during that time. So we need to figure out what is going to be the concentration of O2 at 50 seconds. Well, we need to figure out the change in the concentration with regard to the change in time of O2. So we write the expression for O2. And the expression of O2 is rate is equal to the change in the concentration of O2 with regard to the change in time. And so what does that mean? Well, it means the change in the concentration of O2 is equal to the rate, which is 0.0015 molar per second. So we know the change in concentration of O2 with regard to time is 0.0015 molar per second. We know that there were 50 seconds that took place. So what we're going to do is we're going to start with 50 seconds, and then we're going to use this expression, and we're going to say for every 1 second, there was 0.0015 molar of O2 produced. And we end up with, and I need to get this in my calculator. I had this earlier, but it's 0.0015 times 50, and we end up with 0.075 molar, and that's of O2. All right, and so that tells us the concentration of O2 at 50 seconds. But that does not tell us how many moles. Luckily, maybe not luckily, fortunately, maybe not fortunately, but we have a resource sheet that helps us convert between concentration and moles. If you notice on your resource sheet, you have this equation that says molarity is equal to moles per liter. And what we need to do is we need to solve for moles, represented by the letter N, or the variable N. So N is equal to concentration times volume. We know the concentration of O2 at time 50 seconds is 0.075. What does molar mean? It means moles per liter. And then we're going to multiply that by the volume, which is 2.0 liters. And then what we notice is liters cancel, and we're left with the unit mole. And so this gives us our answer, 0.15 moles of O2. And that's how we get that. And so we had to apply a couple things, but that's not anything scary. All right. And this one I just added in here for funsies. We're looking at the partial pressure of O2 when it occurs at 300K at 50 seconds. And so what we look at there is we find the partial pressure of O2 is going to be equal to nRT over V. We now know the moles of O2 is 0.15 moles. We know that R is 0.08206. It's got units associated with it, liters ATM over mole Kelvin. And then our temperature is already in Kelvin, so we're going to leave it Kelvin. And then our volume is 2 liters. And so what we should end up with on our partial pressure of O2 is somewhere close to 1.8. What are the units? ATM. All right, and that's how we do that. And this kind of brings us to a good stopping point in this lecture because we're going to go over another section looking at how temperature, how the concentration, the temperature, the surface area, and then how catalysts affect the rate of the reaction. But for now, we're going to go ahead and stop at this point, and you can watch the next video on this lecture. But for now, thank you for watching another great episode of Schmidt Chem, and please like and subscribe.